Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have AAS Journal author Anahí Granada with us today.
Hello, hi, Anahí. Frank. How are you doing?
I am doing awesome on this June 8th of 2022 as we shoot this. And so in Phoenix, where I live, the power switch has been hit. We are definitely very warm in the desert, hot in the desert. And where are you located, Anahí?
Well, I'm in southern Argentina. This is Patagonia. It's called Bariloche. Ooh. It's my hometown where I have the chance to work at the University of Rio Negro. And it's been a pretty cold autumn, I should say, so far. And we but then now it's been very rainy and we have floods everywhere.
Oh, okay.
Luckily, we're in the mountains, so everything went to the lakes. But it's
what's your elevation there? Do you know what the
800 meters above the sea level.
Mm-hmm. Mm-hmm. Okay.
Yes, and we have a very nice ski center here. If you want to come at some point, please feel free.
Actually, I do. So I've been to the Southern Hemisphere or South America, actually, Peru. Because my wife is Peruvian. There, I just said that on YouTube. Oops. So I've been to South America several times with the goal of looking at the southern sky, and I've never yet seen it because every time I go there, it's cloudy, and I have yet to see the sky from the southern hemisphere. So it's on my bid bucket. So I may take you up on your offer to come down and I'll see the southern sky from Argentina. That would be great.
Wow, that would be great. Yes, to have you here. Yeah, and I've never been there in Arizona, so I may go at some point.
Well, we will just extend each other some invitations to come and visit.
Sure, sure.
Very awesome. Very cool. Anahí, what do you like to do for research?
Well, I'm very interested, in fact, in B stars. These are rapidly rotating stars that usually have circumstellar disks that form from the material that leaves the star when, for some not still very understood reason, the star loses mass at the equator and then it starts forming through a viscous process a circumstellar disk. And these are very interesting objects because you can have them as laboratories to study stellar rotation, disk physics. So it's very interesting, in fact. Cool. And of course, as many of them are rapidly rotating. And when I say rapidly rotating, I mean close to their critical rotation at the equator, you can have stars really at the extreme. And maybe, perhaps, the first stars were rotating like this. So the subject is interesting, I think, in every areas of astronomy and astrophysics, and it's exciting. I really like it.
Very cool. Very cool. And that is going to bring us to this very awesome APJ article. It's open access, people. You can go get it. It's very the viscosity parameter for late type stable BE stars. And Anahí, take us away.
Okay, well, thank you very much for the presentation. And this is an article that we made in collaboration with Carol Jones and Aaron Sigurd. They are both researchers from Western University in Canada, where I had the chance to be a postdoc some years ago. So this paper, in fact, was somehow born there, maybe 5 years ago, where we started to talk about this, and then we left it, and then we came back at some point because it's an interest.
Indeed. So we have a little bandwidth. We'll just be patient.
See, well, in the introduction of this paper, B stars have been known to exist for a long time. Since 1931, Otto Struve already had a fairly good picture of what B stars were. Like he noticed that the emission lines, the bright lines in the spectra of rapidly rotate of these stars, in fact, were due to the presence of a circumstellar envelope around a rapidly rotating star. So and he already said that it was matter from the star that was put into orbit around there, and so he had a good idea of the picture, and this not far from what we see today. Many things have been understood already, but there are still lots of things to learn about this. For instance, what is the mechanism putting the mass in the disk? What is the mechanism driving the transfer in the disk? And well, here is that we come to viscosity and to the viscous decretion disk model. In the beginning, someone called it the excretion disk model, but didn't. The term didn't catch up. No. Decretion. Well, of course, it's in opposition to accretion disk. That excretion was a good term in the sense of material that is released from the star, which will not come back and which is useless for the star. So in that sense, it is excretion, which is good, I think. But decretion disk gives you an idea of the in the model of that.
We'll be patient.
Physics and the equations that are used. These are in fact the equations of accretion, but considering not that the mass is or that the matter is falling into a star and then somehow going away, but we have an input of are the same, but we have an outward input of angular momentum in the inner part of the disk.
Yes.
And then, well, this model has succeeded in explaining different characteristics of B disks, so it's very successful. But still today, have proved to perhaps show what the nature of the viscosity driving the disk is. It's not clear yet, so it's important to have new insights for this parameter, for the viscosity parameter in disks. In the past years, people have started to study viscosity in disks, but through photometry, through modeling the photometry, the evolution of formation and dissipation of the disk, and values between 0.1 and 1 have been found for alpha in this case. But in this paper, and of course most of those works have focused on early BE stars, which are usually more variable than late BE stars. As I think that now in the first to second page of this article,
early BE stars,
what we do next. B stars, or when we talk about B stars, BE stars, we consider stars that are between A stars and O stars. So we are in the transition between stars with a no wind, almost no wind, removing mass from the star, to the very hot, strong wind stars. So we are in a range of transition between 10,000 Kelvin to 30,000 Kelvin. And of course, you can have different things going there, magnetic fields, winds, rotation, all interacting. But it's in the B range where you see that rotation can show, can approach the critical limit the most. You see a large fraction of stars rapidly rotating. When I say rapidly rotating, as before, I mean close to the critical rotation.
Omega crit. I'm with you.
We focus in this range. And then why late and not early? Okay, early V stars, on one hand, they have strong winds which can interact with the disk and heat it and perhaps produce another input of energy that we do not account here. We just consider that it's not there. But the main reason is that early B stars do not lose matter constantly or smoothly. They seem to be outbursting, or maybe if not outbursting, losing mass not in a very steady way. And of course, they rotate fast, but many early B stars are rotating, have been found to rotate below critical. Let's say 0.8, 0.7. So maybe they require of other mechanisms to put the matter like from time to time, they get this extra energy to put matter.
Patience.
So this extra energy you need is small, and you may have it all the time. This seems to be happening. Late B stars tend to rotate closer to critical globally than early B stars. So
yeah, okay.
They seem to be closer to the critical limit than early B stars. If you take the late B stars, most of them rotate close to critical.
Okay.
Okay. And so then I think that I'm in these points here. Okay, so then, okay, then we assume that once the disk is formed, it's stable and it's Keplerian and it's thin, of course. And this is also observed in many late B stars. You have these very stable disks, which are observed as very stable H alpha profiles or energy distribution. You don't see them changing. Some of them do, but most of them are very stable in time, even for almost 100 years. If you see some of the early profiles published by Merrill 1952 of some of the stars we mentioned here, Delphini, Wendell, that object there has been stable since the beginning of 20th century, not 19th. Right. So these late B stars seem to be in the conditions where we can consider that the angular momentum rates and mass loss rates that we derived in a 2013 paper when I was a postdoc in Geneva, we can consider that these angular momentum rates and mass loss rates hold for these observed stars. We can use these values that we obtained there to model the viscosity parameters for late B stars, because in that paper we assumed that the stars were rotating critical, so we need to be in that assumption in that regime to have this to be able to compare both things.
Cool, very good.
Mass loss rates, which are not directly compared to those values that we found in 2013.
Okay. And we just have a little bandwidth issues. So we'll be patient.
Viscosity parameter for late type B stars. And then, okay, we just put the equations. These are not new equations, and in this part I didn't do really innovation in the equation.
Sure.
This is the angular momentum conservation and mass conservation at some point, and we put them together to find what the radial velocity is and what the viscosity dependent on R is from typical equations used for accretion disks. But where we consider that we have an input of angular momentum in the inside part of the star. So we have what we call a decretion disk. Yes, so we rearrange the equations, we make some assumptions. One of them is that when you have a stable disk, you can consider that the outer radius has a velocity a velocity that is 0.5, the Keplerian velocity. This can be found in an article from Kritichka et al. They obtained this through numerical simulations. So we consider this as the outer radius of the B star, of a stable B star, that has settled and it's steadily losing mass and angular momentum. So under this assumption, we can write equation 8, where you can see that we have the viscosity dependence on R, and it depends on the mass loss rate, on the density, surface density structure, and well, we have the outer radius there.
Yes.
In equation 8, this outer radius is the one derived at Kritichka. Okay, so here, if we look at this equation, we have to mention that we are within R out divided by 4 in order to have the viscosity having a sign that is not changing outwards. And this is the case, in fact, because we want to analyze the innermost region where the observables that we get are formed. So it's within the 20 stellar radii. We are safe to use these equations without having changing the sign and having issues of this way. And then we go to the viscosity parameter alpha. Yes, we find it there in equation 9, which is typically the viscosity divided the scale height and the speed of sound. So many times the isothermal disk is considered. For B stars, it's typical to say, okay, the disk is isothermal. It's 0.6 the effective temperature of the star. It's proved to be a good approximation. But nowadays, more complex density temperatures are used to understand these objects and to better model them. So we can also consider in the speed of sound, we can replace, instead of using we need to have a weighted density temperature in order to be able to have a radially dependent speed of sound here.
Yes.
So then next we continue to analyze particular cases in the sense that we consider, for instance, what happens when alpha is constant, and we recover equations that have already been found in literature many times. So, but when we plug in the numbers that we have, for instance, the mass loss rates that are of the number of the order of 10 to the minus 10 solar masses per year. You see, these are slow. These are not big disks like the ones of protoplanetary disks or other disks. These are very tiny. These are tiny. Excretion disks. This is a small amount of gas going out of the star and forming a disk around. And we have we can have this constant alpha characterizing the disk at some point. And we plug numbers there. We can also put the outer radius corresponding to the star, the stellar parameters that come from what we assume for the stellar models, for instance, the mass and the radius of the star. All of them come from our 2013 papers for the mass corresponding to late type B stars. And then some lines below, you can see that we have values of alpha depending on the density, of course, on the density at the base of the disk of 0.1 to 0.4, or maybe if we can use more adequate densities for each stellar mass, we can have values around 0.4. Or 0.3, 0.4, depending on, of course, on the parameters that we put in this equation. But these are within the values that are known for B stars. Here we mention a reference to Rimulo et al. 2018, where they studied many B stars in the small Magellan cloud, and they found constant values of alpha, but considering a different value of alpha for formation and dissipation phases of the disk of early type stars. And they did obtain values between 0.26 and 0.63, which interestingly, our steady everlasting disks are around 0.5, let's say 0.4 here. Then we can consider, we allow alpha to be variable with R.
Yes.
And then we also consider different temperature structure. We allow it to be isothermal in the vertical direction, but varying with R. It's also usually assumed with the parameter S. And then we also have the typical density structure assumed for B stars, depending on a parameter N radially. And then, we have this also radial variability power loss for the temperature and for the surface density structure. And then we plug everything in again and obtain the variability of alpha for these power law values, and then we plug them in, and we found the solutions that depend on these n and m parameters, and related to the density and related to the temperature. But modifying these parameters can change the shape of the star. But as you see in the exponent of alpha, combinations of n and m can have a similar variability of R. So it's somehow degenerate if you consider, because you can have different n values that give you the same alpha R.
Yeah, same exponent.
Okay, so then, well, isothermal disks, we go here, of course, we came through the general equation, and then we assume they are isothermal, so we have a constant temperature here, and see how, yes, we found how alpha varies. And well, you can see some results in figure 1. We can see how it varies. Alpha changes for different. I allow you to go to the plot here. Okay, so different colors correspond to different masses of the central star. 3 solar masses is in purple. Then we have 4 in green, and 5 solar masses in light blue. And then different traces correspond to different n values. So okay, we find that the value of n equal 3.5, which is the typical values for B stars, leads to almost constant, which correspond to the dotted the dotted point. Those correspond to almost, as you see, roughly constant in the R, which that is a typical n assumed for B stars. So it seems that the constant n may result like a good average approximation, and a value of around, for instance, 0.3 something, and going 0.4, 0.3, and a little bit smaller for the small mass stars. But it's a range between 0.1, 0.15 to 0.40, more or less, roughly.
On alpha.
So we can go back to the text if you want.
Alrighty, let's do that.
So, okay, we've seen that then the isothermal case leads us to have the constant alpha values for the typical n's assumed for B stars. Okay, and then next we said, okay, let's see what about the timescales of these disks. And what we did is, okay, we have the typical expression for the viscosity timescale at a radius r, which we derived to integrate it in time. It's just an expression for the viscous timescale at a radius r. And then we put that in a table as well. And we find that for, I think it's in table
1.
Table 1.
Let's see, table 1.
Table 1, yes, there. Well, these are the alpha values for the the cases that we have just shown, from 0.13 for 0.44, 0. And then we obtain these values. Now we are looking at column 1, 2, 3, 4, 5, 6, 7. I think it's the viscous timescales at 10 stellar radii and 20 stellar radii then. And we see that we are in the scales of years. And these are the variabilities or the timescales related to sometimes the dissipation, or when we see formation and dissipations of disks, of B disks, these are roughly the scales that we observe. So this is interesting, I think.
Tens of years.
Tens of years, yes. And the alpha values, well, you can see how they vary with alpha. And then you can see a column also, which is a magnetic field in the Z direction, which we can see now what they mean and why they may be interesting.
Okay.
If we go back to the text.
Sure.
I think we show some of the expressions a little bit below.
There we go. There we go. 21.
Okay, yeah. Then I hope I haven't missed anything important. I can come back later to this point.
Okay.
But
No, I'm good.
it's very interestingly, Kritička in 2015 gave some expressions for the strongest vertical equatorial magnetic field that allowed magnetorotational instabilities to develop.
Right.
So if our disks led to values that were larger than these, they would point towards against having the magnetorotational instabilities producing the viscosity in these disks. So we wanted to check whether our values made sense in the framework of Kritička. And they said, okay, if they need to be smaller than 10 Gauss, in order to, these are values that they gave, I think, I don't see it here, but yeah, we found that in all cases, our maximum values for the this vertical strongest magnetic field is in all cases is smaller than 10, which is good in terms of the framework of Kritička for magnetorotational instability. So that was a good point to check.
Yes, definitely. Yep, 10 and 20 in table 1. Yep, we just went and looked at that. Very good.
Yes, and of course, these are equations that where we can plug all the data we have and put and get these numbers.
Very good.
Okay, so then we said, okay, we can allow for the density and temperature structure differ from an isothermal or a power law. We can do that with the models that we have now. And this also allowed us to compare what we were finding or to get the alpha parameter for an observed V star, for a real object. And then maybe tomorrow or someday, some other researchers or we ourselves can do the same thing for other late B stars and see if this is found for all of them. And I mean, the same results are hold for all late B stars or not. And also try to understand why we get these values of alpha.
Okay.
So I will go and try to explain why Wandolfini. So we said, okay, let's go and get a late type B stars with a stable disk. And then it came to our minds immediately, Wandolfini. Beautiful late type B star that if you take a look at the H alpha profile, if you go to figure, I think 3, we can, I don't know if it's there.
Oh, there we go. Beautiful. There we go. It's Wandel.
Yeah, Wandolfini on figure 3 with open dots. You can see the H alpha profile. This is one profile. It was it's the same H alpha profile that Jesse Silak used in 2014 when studying shell stars.
Yeah.
But if you take any of any H alpha profile of this star, will look almost exactly the same. Many people have reported that this is stable. This star is stable, except for some authors that have recently, I think when it was Kubat, that found that it may have a small variability. But even if it had a very small variability, it is not something that would change the structure of the whole disk. It's something very mild.
Perturbation.
Of course, it's interesting, but roughly in 100 years, the star didn't lose or form a new disk. So it's it's the same disk. Okay, so we have this stable B star. It's a shell star. As you see the profile, you have this central absorption, which shows you that the material just in front of you is not emitting. It's absorbing light. So it's typically explained and also modeled as a star seen with a high inclination angle. You are almost seeing it equator on.
Yeah.
Where you have a lot of material in the line of sight, which is obscuring the central part of velocity 0. But then you have these 2 wings, very nice emission wings, which of course come from this circumstellar envelope. And then this circumstellar disk. Maybe we can go back to the text now.
Sure.
To see where I'm following the text, as you can see.
It's all good. It's all good. It's an article. We should go through the text.
Sure. yeah, to have in mind what the way that we perceive it. Okay, so we have this very and this is also a star that has shown to have visiting of eye values between 200 and 3020 kilometers per second, which is very fast for a late type B star. So certainly rotating close to critical or not far from critical. So we are under the conditions that we like. So then, in order to get the disk parameters, Aaron Sigurd from Western did some computations with B-disk, B-ray. These are codes usually used for modeling observables in B stars and other emission line stars having a disk, as its name indicates, B disk, B ray. And you have the full solving the full radiative transfer through rays, through a series of rays going through the disk or disk plus star, the star plus disk. Cool. And then you can have the in this case we get the profile for H alpha or the energy distribution. Right. And this way, and of course we need to put inputs corresponding to the stellar parameters and mass and radius and everything to have the well the stellar spectrum, let's say. Yes. Which is the source of photons for the disk. Then, of course, we assume that the star is deformed by rotation. So we have the temperature variability with latitude. Well, typically assumed for B stars. And then we can have a temperature. We can have a disk, and we can have a temperature structure of the disk as well. And this is the temperature that we use, and that which is shown, I think, in figure 2. Was it? It's there. It's up there.
Figure 2. Yes. There we go. And
good. So here you can see how the temperature structure is. You can see that it's variable. You have a colder inner part, and then you have a more heated region. This is also some photons from the hotter polar regions reach this part as well. This one is the coolest part of the star, the equatorial. So you have a complex temperature structure, which we will not use in our viscosity determination. We use the density weighted temperature, which is calculated as you can see the revelations in Sigurd's paper. I think it's 2008. It's referenced there. But basically it's the integration of the temperature at a certain point times the density integrated in Z and derived by the density integrated in Z. So you weight the temperature and you get this beautiful structure that
very nice.
Aaron put here in this beautiful plot.
So very pretty.
We use this is the temperature structure, the radially varying temperature structure that we use, that we plug into the viscosity equation to find the values of alpha for this particular star.
I'm with you. Yep.
And then yes, and then of course we obtained this temperature structure through the fitting of H alpha profiles and also from the energy distribution. This is explained below, of course. A grid of varying density, varying n was generated.
Okay.
Varying also the outer radius of the disk and well the disk parameters, and I think more than 7,000 H alpha profiles were obtained, and then the best fits are plotted in figure perhaps 4. I don't know, it's down there.
4. There we go.
So these are the best fits for the H alpha and the energy distribution. But the family of parameters that best fits, I think it's figure 5. It's below. This is the fitting of the energy distribution.
Yeah, that's the SED.
Yes, that's.
Okay, here's H alpha.
Yes, of course. He took care of the color excess, which we obtained to be 0.13. You see,
Okay.
okay, so we have a cloud of points. The sets are shown in contours, but the best fits in H alpha are found with symbols, with circles. So we have like a banana, or like a region allowed for best fits. But we keep the values that we mentioned there, because they agree also with what is expected for B stars in general. So that's why we kept the values more around here. We have the best values for the energy distributions here, where you find the bluest part, but we also have the H alpha. So that's why we kept values. I think it was a little bit down there. Well, we have a region, but we keep the best values. It's well, now this is just the excess, but it's mentioned in the plots below. I don't have the exact number in my head right now to say it.
We'll find it.
But the best, yes, the best N and density are very really typical values observed for B stars. I think in the plots of H alpha fits, they are shown. H alpha and the energy distribution, 3 and 4.
3 and 4. Sorry.
The best values that we consider are mentioned.
There we go. Yeah, 2 point. Yeah.
And yes. Yeah, here. I think we kept 3.25 value.
Right.
Well, the inclination was well fit. Inclination of 84 degrees.
Right.
So, yeah. Well, we have the whole fitting of the lines, which allowed us to get the temperature structure, which we plug in the alpha equations that we have proposed before. So we find, if you go a little bit below, here it's explained where the data for the energy distribution came. There was from Pickles and Petagne, 2010. The best fitting. And then if you go and scroll down a little bit more, I think I should also already mention this. We also allowed N to vary between 1.5 and 4, which is the range observed for B stars. So here we come to the last plot, and maybe the one that englobes, or that has all the results related to this alpha parameter. If we plug if we plug the temperature structure that we have for the stellar parameters that we consider for Pandolfini, and we allow 3 different values for the angular momentum loss rate. Got it. We find the variable R, in particular in the innermost part of the disk. But then between 5 and 20 stellar radii, it's pretty constant. So it's pretty constant, and it may also be a constant value 0.4, not far from what was obtained for 0.4 in this case, 0.2, 0.1, but these are not far from the values that were derived for isothermal at some point. But interestingly, in the innermost part, we have a variable alpha. And this is interesting because this can be explored, of course, how by trying to model or to explore the viscosity from observables that from here. Let's say hydrogen near infrared emission lines from the Brackett-Thun Humphreys series. These are all formed within this maybe 3 stellar radii. These are from here. So it's interesting that we can, and of course we have other observables. I have this in mind because these are the ones that I usually study, so I have this in mind. But of course, the things that there are many, this can be explored, definitely.
Cool.
So this is work for the future.
Nice.
To this point, those were the results. Okay, so we have these structures. We allow alpha to vary with air by changing the temperature structure. Of course, we fix the temperature structure. We mentioned before that it was somehow degenerative. We change it M, we can plug the N, but here we have a temperature structure and then a density structure, and we have this alpha parameter. So this is perhaps the result. And then, of course, well, we end up by comparing other results in the literature. But basically, of course, what we see is that the values that we get here are in the range of what was obtained by other authors.
Okay.
But most of those authors obtained them from studying variable disks, either forming or dissipating.
Okay.
Early type stars, of course, which tend to be more variable than late type B stars. Yeah. And yeah, basically no, I think to my knowledge, at least up to the publication of this paper, and late B stars have not been studied for the viscosity. So this is interesting in itself. Yes. And well, I think that we have contributed to this interesting field. We have not said anything concluding about the viscosity parameter in terms of the physical mechanism there. Sure. But that is the work for people, other people maybe, or ourselves, I don't know. But we have not said anything about the physical mechanism, but that physical mechanism may need to explain these things. So yes. Yeah, I think that there we go. I think we went pretty fast.
No, it's great. Very good.
Through the article. Yes, but yeah, it was nice. In the beginning, you see the papers are born differently. This paper was born from making some numbers to understand what viscosity would be for late type B stars, and then we realized that there was not very much information for the subject. So it was nice that we could end up doing this and publishing it in APJ.
Cool. Significant new results. Yes. Yes. Very nice. Very nice. Anahí, thank you so much for walking us through your very lovely APJ article.
Thank you, Frank. Thank you very much.
You're welcome. And you touched on it a little bit there. So let me go ahead and follow up on that. So given the published article and the paucity of results for late BE stars, where do we go in the future, let's say over the next 2 to 5 years? Are there additional theoretical calculations that could be done? Are there additional stars besides one DEL that could be added to the analysis, and so on? So just sort of where do we go over the next couple of years?
Well, at least in my interest, of course, having trying to gather all the late type B stars and see what we get for them, I think it's interesting itself. Whether we find the same values of alpha, but of course, as you see in the paper, we allowed the range of L dot to vary. We said, okay, if we divide it by 3, if we divide it by 10, and I didn't comment a lot on that. But why did we divide it? Why did we allow to have smaller values? In fact, there's some work in the literature saying that the values of angular momentum loss rates that we got in 2013 may, in fact, overestimate what is derived from by other people from observations of B stars. But these, of course, all those works were done for early B stars, not for late B stars. So maybe trying to better constrain the angular momentum loss rates for B stars will improve the quality of the alpha parameters that we get, or will allow to better constrain that. So that is one of the things I'm working on, trying to better constrain the angular momentum loss rate, and we are doing that maybe in 2 different ways. With people in Geneva, we have proposed, we have introduced in the evolutionary models the possibility of losing angular momentum before the star reaches the critical limit. At the moment, or in our 2015-13 models, the star lost mass mechanically just when it reached critically. The code inside says, okay, if the velocity of this little amount of mass is above because it's transferring angular momentum outwards, the star.
Yeah.
If we have this reaches a little bit more than the critical velocity, this has to be removed, and it's removed. But now we say, okay, let's allow the star to lose mass before reaching the critical limit, and this is giving interesting results because these give smaller angular momentum loss rates and may work particularly good for early B stars. For late, the values that we got may be fine, but we need to settle this point. And also people from Western, Mohammad Goreishi, who's working with Carl Jones at the moment in Western. He's been working on the determination or to exploring also the angular momentum loss rates through the viscous equation disks, but from an analysis of the disk, from the modeling of the disk itself. Yeah. So this also will improve our knowledge on the angular momentum loss rates that better fit the data.
Cool.
So I think, and I'm collaborating with both groups, so I think my contribution to this will come from the perhaps better constraining the angular momentum loss rates. Mm-hmm. But well, the B star field is very open, and I'm interested in all the different phases, like rotating populations and the modeling of line profiles. It's beautiful. It's very exciting.
I love it. I love it. It's beautiful. It's beautiful. I gotta take that one as a quote. That was fantastic. Awesome. Anahí, thank you so much for walking us through your very lovely article again.
Okay, thank you for the invitation, and I also got to see very interesting presentations. I invite everyone to look at other talks because many of them are very, very interesting. Thank you very much.
Okay, that's good. That'll do, everyone, and I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.
Bye.